Okay, I want to show you guys a simple circuit. So suppose I have a single resistor. We'll just make it 2 ohms. And over here I got some kind of source of voltage. We'll call it VS1. And over here I got another source of voltage. We'll call it VS2. And intentionally I'm showing you, they're really connected. I'm just saying that, I'm just kind of emphasizing that this voltage source, now we don't know the value of VS1, but this voltage source is pushing current this way. We'll call that I prime. And I know it's pushing current that way because we said that if I have a voltage source, current comes out the positive end of a voltage source. And this one over here is pushing current the opposite way. It's pushing current this way. We'll call this I prime 2, I double prime. If I tell you the magnitude of the current, say I say I prime is, I don't know, let's make I prime 5 amps. And let's make I double prime 2 amps. So if I give you the magnitude of the current, see if you can calculate the voltage drop across that resistor. What would be the voltage drop across that resistor? Let me know if you get an answer.
Would it be 6?
It would be 6 volts. The answer is 6 volts. Now, how did you get to 6 volts? What did you do?
Well, I subtracted 5 from 5, and then I multiplied it by the resistance.
Okay, so here, who was that talking? Is that
Nathan?
That's Nathan. Okay, Nathan said he could look at these currents, and just from the picture, you can tell that those currents are pulsing each other. So you got to do a subtraction. It looks like 2 current flowing in the circuit. It looks like a current of 5 amps going to the right and a current of 2 amps going to the left. But in reality, there's 1 current flowing in that circuit. It's the difference between the 2. So what Nathan did said, all right, well, what we'll do is we'll take 5 amps. We'll subtract 2 amps from it. So the net current in the circuit is 3 amps. What I really have is 3 amps flowing that way. And if I have 3 amps flowing in the circuit, the voltage drop is easy. It's just I times R. I take 3 amps times 2 ohms. Well, that means the voltage drop across the resistor is 6 volts. And I don't know if I said this in other classes, but the side that the current enters in will be the positive polarity of the resistor. The side that the current leaves from is the negative. Now remember, the negative and positive on the resistor is not like the negative and positive on the voltage source. The negative positive on the voltage source is always present, whether it's hooked up to a circuit or not. The plus and minus across the resistor, the voltage drop, is only present when there's a current flowing through the resistor, because that's the only way you can have a voltage drop across the resistor, is to have current flowing through it. But you see what Nathan did. He took the difference between the 2 currents, got the net current of 3, and said, all right, if there's a net current of 3 flowing through the resistor, 3 times 2, 6 volts, with the polarity shown. And you would be correct. Let me show you another way to do it, though. What you could do if you wanted to, you can say, all right, I'm going to act like this source over here doesn't exist. I'm going to set that source to 0. How do you set a voltage source to 0? Anybody? How do you set a voltage source to 0?
Shorting it.
Put a short in it.
So if I short this out, then this current over here, that 5 amps, just like this current is not here. That 5 amps would flow through the circuit this way, through that short. And then the voltage I would get would be, I would get 5 amps times 2 ohms. From this voltage source, I have a polarity of 10 volts plus minus. And then we're going to say, all right, well, let's turn this one back on by removing the short. And let's turn this one off by shorting it out. And now I got current flowing that way. Well, the current flowing that way, we said was 2 amps. So if I only had the 2 amps in the circuit, I turn this one off, only the 2 amps are flowing that way. Now my voltage drop is going to be 2 times 2, which is 4. So it's going to be a voltage drop of 4. But it's not plus minus, it's going to be plus on this side and minus on that side. So that means these are opposites, like series opposing. That means I can now subtract these 2 voltage sources, and I get 10 volts minus 4 volts equals the 6 volts that Nathan told us about. And so, I mean, big deal, right? But what we did actually here, guys, is pretty powerful. The way Nathan did it was he just took, like, there was one current going through the resistor, and he found the voltage drop that way. But what I showed you was that we can consider the effect of each voltage source independently. Consider the effect of each voltage source independently, and then add those effects. Well, what do you mean? Well, what I mean is, I said, all right, if only VS1 was in the circuit, if that was the only voltage source in the circuit, I would have a voltage drop of 10 volts. If VS2 was the only voltage in the circuit, and the current 2 amps from VS2 was the only current flowing, I would have a voltage drop of 4 volts. The difference between the two is the actual voltage drop across the resistor. So what we showed was Nathan's way of just dealing with one current is equivalent to the way I showed you, which here we're considering the effect of each source independently, each source by itself. Each source as if it were the only source in the circuit. Now, why am I showing you this? Well, let me show you. So here's what we've done. If you just kind of stand back and look at the semester, guys, here's what we've done. In the first week, we talked about numbers and scientific notation and engineering notation and all that stuff. We learned about the math behind the stuff we want to do for the semester. In the second week, it was physics. We talked about charge, coulombs, the essence of voltage, the essence of current, the essence of resistance, all physics stuff. And only after we understood that did we move on to our first major tool, Ohm's law, and from that, Watt's law. And we use those tools to solve basic circuits. And then we started to ask the question, okay, well, what if I start to put these elements together? Now, so far, the only element you've dealt with is a resistor, but don't worry, we got more coming before the end of the semester. So right now, we're going to look at resistors and how many different ways can I connect up a resistor? And one way is we can connect them end to end. We call that the series circuit. And you know in the series circuit, there's one path of current, and every time current passes through a resistor, it develops a voltage drop across that resistor. And you know, if you add up all those voltage drops, Kirchhoff says the sum of the voltage drops have to equal the total voltage. Kirchhoff's current or voltage law that we got from series circuits. And then we said, all right, well, what if we hook them up in parallel? We had these 2 parallel wires, and we hooked up resistors in between, and we learned there that in the parallel circuit, the voltage is the same across the circuit. In the series circuit, it was the current that was the same. So a parallel circuit has one voltage, but many paths for current. In the series circuit, there was one current and many voltage drops. And just like with series circuits, there was the sum of the voltage drops equals the total voltage. Well, in the parallel circuit, the sum of the branch currents equal the total current or the mainline current. And so Kirchhoff had a second law, Kirchhoff's current law. So you practice doing series analysis, you practice doing parallel analysis, but in the universe, in the electrical universe, most circuits are neither series or parallel. Most circuits is a combination of the two. Most of it, if you take your cell phone apart and you look at, there'll be a lot of stuff you don't recognize, but what you're dealing with is a series parallel circuit. Most circuits are series parallel. And so we put the two together and we started to look at different ways we can approach a series parallel circuit to solve it. And that's kind of where we left off. Well, now what I want to do is go back to that series parallel. What if I have a series parallel circuit? Let me just make one up real quick. What if I have something like this? And I got a voltage source over here. Well, we all know how to solve that, right? If I give you values for the resistors, and you know all the values, what do? We said, well, that's easy. You label the nodes and name them, and then you start at the part of the circuit furthest away from the voltage source, and then you start to combine things, and we work our way down to a series circuit. We solve the series circuit, and we work our way back to the original circuit. Sometimes we have to draw 2 or 3 circuits, but each step helps us solve the next step. So we practiced that the other day. And then we said, all right, well, what if we don't know all the values? What if we're missing the voltage? What if we're missing the resistor? What if I have a series parallel circuit, but I don't know all the values? Well, we said, all right, we got to go to the part of the circuit where we know most information. Usually you can figure out at least 2 things about a component. And we start there, and we use those basic laws and principles and logic to solve the circuit. And we practice a few of those. But what if I gave you a circuit like this, a series parallel circuit, but I added another voltage source or another power source to it? What if I add another battery like that? This is BS2, and this is BS1. And what if I say, all right, now, I want you to find the voltage drop across each resistor and the current through each resistor. With what you know so far, you couldn't do it. Just using the tools of Ohm's law, Watt's law, Kirchhoff's law, you couldn't solve it. So what I want to do now is spend the next couple of sessions, couple lectures, looking at ways of solving series parallel circuits with multiple voltage sources or current sources. We haven't talked a lot about current sources. I did mention it. One of your homework problems dealt with it, and you'll see it again on exam 3. But a current source is another type of power source. So what if I gave you something like this, but I have multiple power sources? You couldn't use Ohm. The only way you can use Ohm's law to solve it was if these 2 sources were in series. If they were in series, it would be a non-problem. If I move it over here, and I put another voltage source right here, if they're series aiding, I would just add them up and replace the 2 with 1 voltage source. And if I flip one over, the series opposing, I would subtract them. The polarity of the net voltage would have the polarity of the bigger voltage source, but again, I can combine the 2 down into 1. So if they're in series, it's not an issue, it's not a problem. But what if they're not in series? What if these voltage sources, I got one here, and I got one here somewhere else in the circuit? How in the world would you solve that? And unfortunately, we can't use Ohm's law and Watt's law directly. We have to resort to more powerful techniques. And at the beginning of this lecture, I kind of showed you one. I showed you that with a simple resistor, what you can do is you can actually take a circuit. Let's say you have a circuit with, just for an example, with 2 voltage sources. I proved to you, between what I said and what Nathan said, I proved to you that you can take each voltage source and consider the effects of each voltage source independently and add those effects to see what's actually going on in the circuit. So what I'm saying is we can do with this circuit exactly what we did with that very simple circuit at the beginning of the lecture today. We can turn one voltage source off. How do you turn a voltage source off? You turn the voltage source off by replacing it with the short circuit. So if I turn V2 off, if I replace it with a short, then what I have is, you guessed it, I got a series parallel circuit that you know how to solve. Solve this series parallel circuit for the voltage across R1, the voltage across R2, the voltage across R3, the current through R1, the current through all the resistors. We can solve with only S1 in there. And then we take those current values and we just kind of look at those. And then we turn BS1 off and turn the other one back on to see what current and voltage drops it produces. And we add those voltage drops and we add those currents to find the actual effect. So if I have a current going this way from this voltage source and a current going the opposite way from the other voltage source, you know you would subtract those 2 currents. I mean, the picture shows you that. If I have currents going in the same direction through a resistor from 2 voltage sources, logic would suggest you would add them. If I have polarities from one voltage source, let's say polarity for R1 was this way from this voltage source and the same way from the other voltage source, then I would add those polarities. I would add those voltage drops. But if they were different, I would subtract them. What I'm describing for you, and I know I'm saying a lot, but it's going to be really easy when I show it to you. What I'm describing to you is our first method for solving series parallel circuits with multiple voltage sources. And this method is called superposition. Superposition. And that superposition kind of comes from the idea that if I have like a current going this way from one voltage source and a current going this way from another voltage source, you can superimpose those currents. If they're going opposite ways, that means there's a subtraction. If they're going the same way, that means there's an addition. You can superimpose currents and voltage drops to find the actual current through a device or the actual voltage source across a device in the circuit if you have multiple sources. And so that's what I want to look at today. I want to look at an example of how you would use the method of superposition to solve circuits with multiple voltage sources. So let's look at our document and see what we have. Okay, so one theorem we learned about was Thevenin's theorem. So we looked at Thevenin's theorem and we did some practice. That was this first topic here. And then with Thevenin's theorem is this kind of like a sister theorem called maximum power transfer. And we learned about maximum power transfer. That's what happens when the Thevenin resistance, which is the resistance the load sees, and the load resistance, when they're equal, then you get maximum power transfer from the voltage source to the load. And then you did that power lab. In that power lab, I don't know if you look at the data yet, but in that power lab, you're going to actually prove maximum power transfer theorem. Because when you actually graph, when you make the graph in your power lab, then what you expect to see is maximum power in the circuit when the potentiometer rheostat that you adjusted in that lab, when that resistance of that device equals, I believe the other resistor was 2.7K, when those two resistors are equal to each other, you expect to see the power peak. So without really knowing it, you kind of prove maximum power transfer theorem, or you will when you do that lab on power that we did the other day. So today I want to talk about this theorem, the theorem of superposition. And so in the last class, we talked about a very famous and very useful circuit. We called the bridge circuit, and I kind of gave you a thought experiment. I told you about my grandma's Cadillac and how it had a leveling control in there, and how I went off and thought about if I wanted to reproduce that, how would I do that? What would I do? And then this bridge circuit was a nice solution to that. So we talked about that. If you didn't get a chance to watch that video, you should go back and watch it, because that bridge circuit is a very, very useful circuit and a very, very common circuit. But what I want to do now is the next circuit on this sheet. So if you have the handout, you might want to take it out. If not, I am sharing the document with you right now. So look at the bottom. Look at figure number 2 on the bottom. What you see is a couple things. Number one, you see a circuit. Now this circuit is drawn a little differently. I don't know if you've seen a circuit drawn this way before, but notice I don't have the wire. There's a wire that actually connects these points right here. And normally we show that wire. We show that wire. But what you see here without the wire is kind of a shorthand way of drawing an electrical circuit. Sometimes in digital electronics or in your circuit, your electronic circuits courses that you would take, the circuits become so complicated. Anytime you cannot draw a wire, you don't do it, and it just makes the circuit look cleaner. So this is just kind of a shorthand way. But the way I'm showing the circuit, if that bothers anybody, then feel free to go ahead and put that bottom part in like this and connect the bottom parts of the components. But what you see here is you see the symbol for ground. And since all these symbols for ground match each other, that what they're showing you is that there's an electrical connection between these. You're just not showing. So I'm going to leave this as is. I'm going to reproduce the circuit as is. But I want you to understand what this circuit means, the way it's drawn. And what we have is a circuit, it's a series parallel circuit. We have 3 100 ohm resistors, and we have 2 voltage sources. We have a 10 volt source, VS1. We have a 5 volt source, VS2. And what I want to know is, according to the problem statement, it says find the current in R2. What's the current in this resistor? Well, there's no way to do it just using Ohm's law, because you got to know what effect both voltage sources have on R2 in order to solve for the current through R2. So one way to do that is the method I just showed you, the method of superposition. And to do that, what you do is you turn one of the voltage sources off by replacing it with a short circuit. let's say I want to turn VS2 off. So I would short this out. When I short that out, what that does is it basically places R3 and R2 in parallel, because remember they're tied together through this ground. So if I short that battery out, then R3 and R2 are in parallel, and I got a series parallel circuit that I know how to solve. So then what I would do is I would solve for the current through R2 with just this VS1 in the circuit. I figure out how much is the current through the resistor. And once I determine that, then what I would do is I would set the other voltage source equal to 0. And then I would figure out what would be the current through the resistor from the 5-volt source. And then if the currents are going in the same direction between the two voltage sources, I would add them. If they're going in opposite directions, I would subtract them. That's the method of superposition. Now you can read the actual statement of the method in your book. I'm not going to paraphrase it. I think it's better to just see how it works, and then you'll understand it. So take out a sheet of paper. You'll need paper, you'll need pencil or pen, coloring pencils or pens, and if you like to draw straight lines, you'll need your straight edge and the calculator. And what I want you to do is to draw this circuit in the upper left-hand corner of a piece of paper, and let's just kind of walk through how we would solve this using the method of superposition. So take out a sheet of paper and draw the circuit. Okay, so by now you should have the circuit drawn on your paper, and the method goes like this. We're going to turn one of the voltage sources off, and the way you turn a voltage source off is by replacing it with the short circuit. The way you turn a current source off is by replacing it with an open circuit. I got 2 voltage sources, so I'm going to turn one off and leave the other one on. I'm going to figure out, what we want to know is how much current is going through R2. I'm going to figure out how much current is going through that resistor with just one of the voltage sources active. So I'm going to turn the 5-volt off by replacing it with the short circuit. So it's going to look like this. When I do that, then the circuit I get is this. I get a 10 volt, which I'm leaving on. I got that first 100 ohm, which is R1. I got the second 100 ohm, which is R2. So here's R1, here's R2. That's 100, and that's 100. And then I got this second resistor over here, but I've taken that voltage source out and taken it out and grounded it. So that 100 ohm, which is R3, when I replace that voltage source with the short, it makes R2 and R3 in parallel. If you can't see that they're in parallel, just move R3 down to the side like that. Just draw it over here like this. And you'll see they're in parallel. And so by turning this voltage source off, we're going to say, all right, well, how much current flows in R2? So I'm going to give you a few minutes to figure that out. See if you can calculate the current through R2 with only VS1 in the circuit. I'll be quiet for a minute, let you work it out. and we'll talk about it. I'm going to give you one more minute, and then I'm going to talk about how we would solve this circuit for the current through R2 with only VS1 in the circuit. 1 minute. Okay, let's have a look at this. So the method was turn all the voltage sources off in the circuit, or current sources off in the circuit, except for one. In this circuit, I only had 2 voltage sources. if I had 5 voltage sources, I turn 4 of them off and leave 1 on. And what I want to do is whatever I'm looking for, current, voltage drop, whatever it is, find that quantity with only 1 voltage source in the circuit, with only 1 active. Figure out what that is, and then turn that one off, and then make the next one active. And then you're going to add up all the currents and voltage drops. If the currents are going the same way, you add them. If they're going opposite ways, you subtract them. If the polarities are the same way, you add them. If they're reversed, then you would subtract them. And so by turning off VS2, by shorting it out, what I've done here is I've turned a circuit with 2 voltage sources in it, which we don't know how to handle, to something with 1 voltage source in it, which we do know how to handle. And I'm going to figure out, all right, what is the current through R2, magnitude and direction from that 10 volt source? What is that 10 volt source doing for R2? Well, we have a series parallel circuit. How we solve series parallel circuits? We learned that we identify the nodes. We name the nodes. Now, normally I would have a node A or node B, but when I use this shorthand way of showing the circuit, I just usually just draw 1 node. So instead of having another node, my other reference node is assumed to be down here. So I'm going to call this node A. So I label my nodes, I named them, and now I'm going to start from the part of the circuit furthest away from the voltage source. I'm going to start combining stuff until I get down to a series circuit. In this step, in this case, I can do it in 1 step. I can combine R2 and R3 in parallel, and then the series circuit I end up with is this one. This resistor here is R2 parallel R3, and my node A is in this corner right here. If I take 100 and parallel 100, that gives me 50. So that equivalent resistance is 50 ohms. And what I want to do now, solve the series circuit, and then use that information to help me solve my original circuit. So let's solve the circuit, solve the series circuit. You find the total resistance. Well, the total resistance in this circuit is 150 ohms. Then we find the total current by using that total resistance and the total voltage. So my total current would be my total voltage divided by my total resistance. How much is that? 10 over 150 is what?
I got 0.06 amps.
0.06 amps, which is equal to 60 milliamps. So current in this circuit is 60 milliamps. And then I want to show it in my original current, in my original circuit. The current in the series circuit is the main line current in the other circuit. So I know that that's 60 milliamps. And what else can I find? Well,
I got 66 milliamps.
66. Okay, 66 milliamps. And anybody else get 66? Is that checking out? Is it 60 or 66?
66.7 is what I got.
66.7, so now we're saying 67. Okay, we just keep going up, don't we? I wish my bank account did that. So we're saying 67 now, so
Yeah, it would be 67 if you round up.
let's round up. All right. So we got six. Now what else can we get? Well, we can get the voltage drop. So somebody give me the voltage drop across, well, we don't really, since the resistor we're worried about is connected to node A, which is right here, we don't really have to find the voltage drop across R1. I mean, you could, but the information we need is in this one. So give me the voltage drop across the 50 ohm. What would that be? I
Would it
need
be
the voltage.
3.35?
How much?
Would it be 3.35 volts?
You said 3.35? Is that what you got? Anybody else get that? 0.067 times 50, is it this number?
Yes,
According
it
to
is.
it is, okay. Now, according to my screen guys, there's 16 people out there, so I should have 16 calculators doing this at one time. So you make sure you're doing the calculation. Now, remember what we said about series parallel circuits. This is a node voltage, which means in the original diagram, when I show it, I want to show that 3.35 volts going between the two nodes, node A and then my reference node. So now we know the voltage across the resistor that we were interested in. I can easily find the current through it. I guess I'm making current blue. So the current through this resistor is just going to be the 3.35 volts divided by the 100 ohms. And that's going to give me, what is that? 0.0335 amps. That's going to give me 33.5 milliamps. Does that look right to you guys?
Yes.
Okay, so
Yes.
here's what I've done. I'm not saying the current in R2 is 33.5 milliamps. I'm saying that the current contribution from the 10 volt battery is that much. I'm going to show it going in this direction, and it is 33.5 milliamps. So now guess what we do? What's the next step?
Well, we know that since both resistors are the same, it's the same going both ways.
Well, we've actually achieved part of our problem, right? We want to know the current. What we're trying to do is solve for the current in R2. And so superposition says that I can look at each source independently. So we know the current from the 10 volt source to R2 is going to be 33.5. So now what do I want to know? I want to know the current from the other source. And if those currents are going in the same direction, then we're going to add it to get the actual current. If they're going in opposite directions, we're going to subtract them to get the actual current. So the next step would be this. I'm going to turn this source back on by removing the short. I'm going to turn this one off by replacing it with the short. And I'm going to do the same calculation again. This time I'll be finding the current to R2 from the 5 volt source. So your circuit is going to look like this. You're going to turn this one back on by removing the short, and you're going to turn the other one off by replacing it with the short. And then you're going to do the same analysis, but this time, this is the active voltage source, this one is set to 0. You do the same analysis and figure out how much current is this sending to R2. And then you're either going to add or subtract those net currents to find the actual current in R2. So you go ahead and do that. I'll be quiet. I'll leave these notes on the board. You go ahead and do it and see if you can work out how much current is that 5 volt source sending to R2 if it were the only voltage source in the circuit. Guys, I'll give you one more minute, then I want to see what contribution for current the 5-volt source has for R2. And then we'll put the two together and see what superposition actually finds out for the actual current. So about one more minute, then we'll talk about it. All right, so what we've done here, we set VS1, the 10-volt source, to 0 by replacing it with the short circuit. And now I'm going to draw the equivalent circuit. So what I have is, I got R3, which is 100 ohms. And then connected to it, I have VS2, which is 5 volts. And then when I put this short circuit here, that forces R1 and R2 to be in parallel, just like before. And if I have 100 parallel 100, I get 50. So what I have is an equivalent circuit that looks like this, where this would be R2 in parallel with R1, which is 50 ohms. If this is my node A, and that would be right here, node A. So last time I solved this series circuit, we solved it using Ohm's law. I'm going to do it a different way. Well, this time we'll use voltage divider rule, and we'll go straight to the voltage across the resistor. So to get to this circuit, what we've done is I have I've had R1 and I have R2 in parallel, and I have R3, and I have the 5-volt source. So that would be the circuit that I get my equivalent circuit from. Okay, so let's solve the voltage at node A, which node A then is right here. Using, let's just use voltage divider rule. In the last circuit, we used Ohm's law. Voltage divider rule will be a little bit quicker. I want to know the voltage across this 50 ohm resistor, so I'll put that in the numerator. Then I divide that by the total resistance in the circuit. I get 150. And I multiply that fraction by the total voltage. And that'll give me the voltage I'm looking for. So that crosses out, that's 1/3 of 5. What's 1/3? What's 1/3 of 5? How much is that?
1.65.
1.65 volts. And if I have 1.65 volts, I forget which color I was using for voltage because I erased it. I guess I'll use green. So we got 1.65 volts from node A to ground. So that means I have 1.65 volts across here because this is node A. And what I do, I want to find the current in R2. So I want to find the current in this resistor. Since R2 is 100 ohms, and that current is real easy to find. To find that current, I'll just take the voltage across the resistor divided by the value of the resistor. And I think when you do the math, you'll get 16.5 milliamps. So this gives me 16.5 milliamps of current going down. So over here in the original circuit, using a different color marker, I'm going to show the current from the 5 volt source as 16.5 milliamps going down. So what's the actual current in the circuit? What would I do to get the actual current?
You would add 33.5 and 16.5 and get 50.
Okay, if I add 33.5 and 16.5, how much is that?
50 milliamps.
I got 50 milliamps in this resistor. The actual current is 50 milliamps. And at that point, if you want to know the voltage drop across the resistor, you can get it. 100 times 50 milliamps. If you want to know the power dissipation of the resistor, you can get it. I can use I squared R, V, whatever you want. Now I found the voltage drop and the current across, and I can actually do this for all the resistors in the circuit. So even though I have more than one voltage source, when I get to the final circuit and I add up the net effects, I end up with the voltage across, the actual voltage across the resistor and the actual current to the resistor. And I can use that then to find power if I want to know it. Now you cannot do this. You cannot find the power in this circuit and put this over here and then find the power with the other voltage source and put it and then add the powers. You can't do that. It works with currents and voltage drops only. You can't find the individual powers by turning one voltage source off and find the power dissipations for the one that's active, and then turn the active one off and the other one back. You can't do that with power because power is not a linear function. You can only do this because we're dealing with linear functions if you know what I mean by that. If you don't, just remember power is a no-no. But now I can solve for any voltage drop or current, no matter how many voltage sources I have. All I got to do is consider the effect of each source independently. Okay, well, you guys did a good job on that, but there's another part to this. If I go back to the diagram, look at, there's a question at the bottom. So if we zoom in on this, look at what he's asking now.
Okay.
Down here.
Can I ask you a question, sir, please?
Yeah, let me answer this first, then you can ask my question.
Okay.
Read this statement down here and tell me what will happen. It says, determine the current in R2 if the polarity of VS2 is reversed. Well, think about it. The polarity of VS2 is reversed. If I flip this over, what effect will that have on the circuit? If I flip this over,
Wouldn't you have to subtract the two values?
Yeah, because now my current, instead of going this way, I have the current 33.5 going down. That's from the 10 volt source. If I flip this over, now the 16.5 will go up. And then I would have to subtract the two. But again, I can still get to the answer. Does that make sense to everybody?
Yeah.
Okay, and now somebody had a question. Was that
It's Riley.
right? Well, I shouldn't even talk to you, Riley, because you don't have your camera on. You usually have your camera on. Okay, what's your question, Riley?
So my question is about the first circuit. So I think we have a source of 10 volts and the total resistance towards 150.
Yes.
So by dividing 10 over 150, so where did you get 67 amps? I mean 67 milliamps.
Well, are you talking about
The first
okay.
circuit,
You can't.
He's talking about the first current.
the first quarter.
Okay. And what's your question again about the first current?
So we had 67 milliamps while we had 10 volts for the voltage circuit and 150 for total resistance.
I'm still not understanding your question.
So I mean,
Because you
you
move the decimal. So like the answer is 10 divided by 150 is 0.066667. And then to get then the milliamps, you just move the decimal 3 spaces and you get 66. But then you round up to 67, so they just rounded up to 67 milliamps.
cool, I got you. Thank you.
No problem.
Okay. Thank you. I didn't understand, but thank you, whoever answered that.
No
Okay,
problem.
guys, isn't this cool? This is a really this is good because now there's a whole bunch of type of circuits you can solve. So we have done series parallel. You've only done a few of them. Just because you move to something else, we move to Thevenin, doesn't mean you've done enough series parallel. You want to practice that. We've done Thevenin, and we've done, 4 or 5 Thevenin problems. We Thevenized the bridge. But again, you haven't done enough. Look in your book, do more series parallel, do more Thevenin. Now we've moved to series parallel circuits with multiple voltage sources, and we'll learn different ways to solve it. We learned one way today, the method of superposition. We've only done one problem, though. Guess what you have in your book? You have other problems you can go to and practice this. When we come back together on Monday, we're going to take superposition and Thevenin and put them together to solve a circuit. So over the weekend, if you have some spare time, if that really existed, spare time is like spare money. At least with me it is. I don't have either one.
I don't have either.
Right. You know what I'm saying? So, but try to squeeze this in, practice this, get good at this, and I think you guys will be amazed at what you can do with this. Okay? Anybody have any questions for me before we sign off?
I just have one question. He
Sure.
can go first because mine's unrelated.
Mine's unrelated too. I was going to ask about your shirt. Got a Kentucky.
Okay, go ahead. What's your question?
Is your shirt Godzilla with a Kentucky face?
You know what? I don't know. I think that's a horse. My mom.
Oh, it's a horse. I couldn't see the bottom of it before.
Yeah, my mom gets this stuff from the Goodwill. You guys worry about how much money you spend for clothes. I worry about how much I don't spend. So I shop at the Goodwill. This came from the Goodwill, so I don't know what it says. I could be advertising anything. It says Kentucky bread. I wear this shirt and people ask me all the time, "Are you from Kentucky?" Because it says Kentucky bread, but no. So it's just an old shirt from the Goodwill.
It's
awesome.
Yeah. Anybody else?
Yeah, I just have a question about attendance. So I've been in class for the past week, but I've also forgot to send the text for the past week for each class.
Yeah.
Is that gonna?
So no. So here's how that works. Now I shouldn't tell you this because in every class you want to make sure you get on the attendance roster. But the most important time is the first 2 weeks and like the last week or two in class. In the first 2 weeks, let's say you forgot. And in week 3, you start sending attendance. Well, when I turn my roster in after the second week, I have to check that you didn't come to class and you get dropped from the class. So you're good on that. Now, at the last week, I got to look at that roster again to see if you've been in class, and then that's when I turn that in. So if you miss in between, it's not going to hurt you. And guys, you really can send me attendance at any time. Let's say you forget to put it in. You think about 11 o'clock at night tonight, just send it whenever you think about it. Try to send it together because it's easier for me when I search the class. If everybody's name, what I do is I go to my Google Voice and I put a class in and all the people come up together in the search. So it's easier if you do it that way, but as long as you get it in there, you'll be okay. Like you can still send it right now, you'll be fine. You can send it tonight, you'll be fine. So no, you're okay. You're still in the system.
Okay, thank you.
No problemo. So, John, I see a picture on your wall. Is that something your daughter did?
Yeah.
Well, I thought you were supposed to hang those on the refrigerator.
Yeah, well, you know, we hang our children's art all over the house, and it's my son's hand and her feet.
Oh. Okay. Okay.
Yeah, otherwise you have a really big hand.
I asked you the other day. You said you didn't know what the talk to you later was, but wait till you get teenagers. You'll learn all of that. Spencer, what's your?
Yeah, I was just like, what does that mean? And then I was like, it took me a couple seconds, and then it hit me, and I was like, I am just so out of the loop. It's unbelievable.
I hang around a lot of teenagers, so I'm not good at it.
I don't know if that's good or bad.
What is this hat on you, Spencer? Vans? Are you a van guy? CA Van? Oh, okay. What's that mean? Is that just a designer hat or something?
Yeah, Vans is just a brand.
Okay. See, John, how out of I am? I didn't know that was a brand. I shop at the Goodwill.
It's just California,
So do I.
New York.
That's all I can afford with kids.
Did you ever make it up to Waynesville?
No, I didn't go to the hardware yet. I think I'm going not this weekend. I got too much going on, but I'll probably make it up there next weekend. I got to go up there and get a mailbox cover. Don't tell me they're closed. Now, you're not going to tell me.
No, you got to go get that food, man.
I'm going. And I'm going to report to you. You'll be my first. You'll get a report from me on how good it is.
It's amazing.
Hey, I'm going to try. Hey, Spencer, am I looking at some stained glass behind you? Is that stained glass or is that a picture on the other? Yeah.
Yeah. I'm at my grandma's house right now.
Is that an old house?
Yeah, but this section they actually built themselves, and they added that part in.
Oh, so that's not an old stained glass window. That's not an old window. That's
this entranceway is where the main part of the house started, and then they added this living room area in.
Okay.
They wanted a second porch or something. I don't know.
I got you. So I have a couple rental properties, and some of them are made in the 30s. And I don't know if you're familiar with rookwood. It's a type of tile, and it's worth a fortune. And sometimes you find those old stained glass windows in the houses. It could be worth a fortune, but I just thought that might have been an old one. So.
Could be.
Okay, guys. Well,
Have a great weekend.
Yeah, and Spencer, when I go up there, I will let you know, and then you'll get a full report from me. Thank you for asking. See you guys later.